Find the current Ix, this one, as a function of time, in the circuit with the ideal transformer of the figure shown. This ideal transformer. Observe the position of the polarity dots on the two sides of the ideal transformer, this dot and this dot here. The first thing we observe is that the voltage on this side, when that has this polarity, the voltage on the other side has that polarity. That is the meaning of those dots there. Also, when the current is entering the dot on one side, let's say on the left-hand side, when the current flows like that, the current is leaving the dot on the other side. Now let's go with the transformation ratio, which is 3. The right-hand side is the high voltage side. So, the low voltage side is this one. The voltage is unknown, but I'm going to call that by any name I want. I will call that V1. Why not? V1. That means that the voltage on this side, on the right-hand side, is 3 times V1. Unknown, but 3 times V1. And the current is higher on the lower side, so the current will be higher on this side, on the lower side, on the left-hand side, and will be smaller on the high voltage side. It's unknown. I'm going to call that IA. So it's 3 times bigger on the low side. This is 3 times IA. We have taken into account the transformer 2 equations. We will write Kcl equations for this node here on the left and for that node there on the right. And let me assign voltage symbols for them. The voltage here will be, well, look at that. If I choose this node as my reference, then the voltage here will be the same voltage V1. Let me call this V1. And the voltage in this other node, I could give it a different symbol name like V2. But why? Observe that this voltage V2 is just the negative of 3V1. According to that polarity, the voltage here is negative 3 times V1. Ready for Kcl branch currents. I will assume this current is flowing like that. Why not? This is given, and this is given, and that's already given. We have chosen that, so I will assume the current flowing like this. You know, it's arbitrary, that choice. And we're ready to write Kcl equations for this node on the left. Currents going in only this one, the one on the left. Currents leaving 3 times IA, and Ix on the top. But because I prefer to work with letters and symbols, I will call the voltage source Vs. This resistor I will call just R1, the capacitor C. This other resistor will be R2. 4 symbols, so I can write now the Kcl equation of this node as Vs minus V1 over 2. Let me write that. Vs minus V1 over R1, sure, over this resistor. That is equal to currents leaving this one 3 times IA, leaving, plus the one on the top, which is Ix, but actually Ix is V1 minus 3V1, that is 4V1, divided by 1 over SC. We know that the impedance here is 1 over SC. So this would be, I repeat, V1 minus 3V1, that is 4V1, divided by 1 over SC, and that is just 4V1 SC. And now the Kcl equation for this other node. Currents entering, only the one on the top, only the current, right? Which is this term. Currents entering, 4V1 SC, and leaving 2. This one, IA, I sub A, and this one. You say, but this current is this voltage, negative 3V1 divided by R2. Sure, negative 3V1 divided by R2, and we solve that system. And we need, in reality, to compute only V1, because with V1, we can use this formula here to compute 4 times V1 SS, which is Ix, the current that we're looking for. For this, I will use the HP50G, of course. And from the HP50G, we get that the current Ix is given by this expression, which is a function of Vs, R1, R2, C, and S. Vs, R2 is 6 ohms, R1 is 2 ohms, C is 1/20 farads. The question is, who is S? S is J omega. Omega over here is 2 radians per second. So S is J2, or in rectangular form, 0,2. What about Vs? Well, Vs is the phasor that represents the voltage source. If we use an RMS phasor, an IEEE phasor, which is usually what we use in the power industry, when we solve for Ix using that expression, we get the RMS value of the current Ix, and that would be fine. That is a value an ammeter would read. But in this case, what I want is √2 times that value, which is the peak value I can use in the function of time. So we realize that is Vs is already multiplied by √2. That is, if Vs is given by the peak value, I get the peak value for Ix, and that is exactly what I've done. I've represented Vs as 2, just a real number 2, 0 degrees, and substitute everything there, and we get the value of the current as a phasor with a peak value of 0.1562 amps and the phase shift of 51.34 degrees with respect to the voltage source Vs. If we write that as a function of time, we use that peak value, 0.1562, cosine the same frequency 2 times t plus the angle 5134 times pi divided 180 to turn that into radians, and those are amps, and that was the solution of question 1 in the final exam. Thank you very much.